What we'll be talking about for the next, quite a bit actually, is using this idea of a vector to represent what we're doing. And if you remember back, a vector has a magnitude and a direction, as opposed to a scalar, which was just a magnitude, a number. So our vector is simply going to be represented by an arrow. The length of that arrow is the magnitude. The direction is whichever way this arrowhead is pointing. So this would be, say, 25 meters per second to the east. But it could be force, it could be displacement, anything with a magnitude and a direction. The good thing is vectors can be added or subtracted. As long as you're in the same plane, it's relatively easy. So if we were in the x-axis here, and I was rowing my kayak, paddling my kayak at 10 meters per second, and I had a 2 meters per second current with me, then the resultant vector, I'd actually be going 12 meters per second in that same direction. Okay? If the vectors are in the same direction, simply add them up if they're going the same way. If they're going opposite directions, if this was my 10 meters per second, and for some reason I was paddling upstream and it was, and I was fighting a current of 2 meters per second, my resultant would only be 8 meters per second. You can think about it if you've ever ridden a bicycle in Texas into the wind. This is a headwind here. This is a tailwind here. Okay? So when vectors are in the same plane, you simply add or subtract them up to get the resultant vector. Vectors at right angles don't pose a big problem. This would be like flying to Chicago, heading straight north, right? There's our north. If we were flying to Chicago at, 400 kilometers per hour, okay, and then we had a wind coming out of the west at, say, 100 kilometers per hour, we'd actually be getting blown off course. Okay? In our resultant vector, if we didn't make any changes along the way, we'd be going that way. I didn't draw that very well. We'd be going that way. We'd get blown off course quite a bit. Okay? Fortunately, airplanes have computers on them that make course corrections virtually instantaneously, so they never get off course. Okay, so now how do we find this here? How do we find that? Well, remember back to your Pythagorean theorem, where you have a squared plus b squared equals c squared. Okay? So you'd have a squared plus b squared equal to c squared. So just plug those numbers in. In this instance, it would be 400 squared plus 100 squared equals c squared. It's a relatively simple calculation on your calculator. Don't forget to take the square root at the end so you can get the actual value instead of the square of the value. Component vectors have two parts, an x component along the x-axis and a y component along the y-axis. That's why we've been breaking everything down into x's and y's. Okay? If you look here, this would be your y component here, this would be your x component here. Okay? The resultant was here. Okay? So what happens if we go backwards now? Okay? What happens if I give you a vector like that? What are we going to do? Okay, well, what you're going to do is set up your own coordinate system. Okay, wow, I didn't do very well with that at all. Set up your own coordinate system, okay? And keep everything along the X and the Y. And I'll show you how to do that. Okay, how to draw the X component. Well, when you're drawing the X component, draw yourself an X-axis in here. Okay? You can actually draw yourself a Y-axis in here if you want to right now as well. Okay? You always draw your coordinate system based upon where the vector tail is at. This is the tail, this is the tip. Tip will show you direction. You know, some of the things we then know is follow the tail of the vector down. Okay? If we follow that down to our X right there, okay, we've basically got our two components, and you can actually follow it along this way as well. So what would happen here? Okay, here's our X component. Let's say our velocity in the X. Here's our Y component, say our velocity in the Y. We use the X and Y, you know, whether it's a force or a displacement or whatever, just to show us which end, which component vector we're working with. Okay, and you notice that those are the same over there and those are the same over here, right? You've got yourself a parallelogram basically, and your resultant is the diagonal of that parallelogram. But if you're given the resultant, here's how you break it down. So to draw the X, follow that tip all the way down to the X-axis. How to draw the Y? Well, follow where you stopped on the X-axis straight up from the tip. Same thing's going on, okay? If you put in your coordinate system, okay, there's your Y component. Okay, your original vector is now the hypotenuse. Here's your right angle, okay? And you have your X and you have your Y. Now how are we going to solve for that? Okay, you're going to have to go back to some trig functions. Okay, here's what it looked like. And there's your right triangles formed right there. So if your hypotenuse is 316 and there's your angle of 35 degrees, okay, can you figure out, can you tell me what that Y component is, and can you tell me what that X component is? Use your trig functions. Okay. Your theta is the angle between the vector and the X. Keep it standard. Keep your angle with the X-axis. That way you won't get lost in the trig functions. So you know the sine is opposite over hypotenuse. The cosine of that angle is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay? So we either have to give you this resultant here at an angle, or we got to give you the X's and the Y's, okay, in order to figure out the resultant. But if we give you the resultant, we usually give you that angle as well. Okay, so in this instance our X component is the adjacent side, our Y component is the opposite side. Our original force is the hypotenuse. Okay, so here to get the X, cosine theta is adjacent over hypotenuse, plug them in, and you get 316 cosine 35. Remember to have your calculator in degrees, not radians. Okay, radians was a different form of measurement, and your angles are, your ultimate answer will not be incorrect, but it's not what we want to use. Okay, to get the Y component, the sine of theta is opposite over hypotenuse, so there's your sine of 35. and your answer comes out to be 181 newtons. So when you find these components, draw yourself out a picture, okay, using the arrowheads, you know. If there's your original one, if you want the x and the y, well, there's my x component, there's my y component, there's my theta, here's my right triangle, okay, and fill in the information of what you know. Okay, you can actually check your work by using the Pythagorean theorem, and as long as you haven't rounded along the way, you'll be getting some good answers.